charged clouds in a nonpolar molecule are constantly moving. It often happens that more of the charged cloud is on one side of the molecule than the other. As a result of this, there are forces of attraction between the positive end of the dipole in one molecule and the negative end of the dipole in a neighboring molecule. These dipoles are always temporarily because the electron clouds are always moving. The attractive force between the positive charge on one molecule and the negative charge on the neighboring molecule causes a weak attractive force between the molecules. Propanone has a higher boiling point than butane. This means that more energy is needed to break the intermolecular forces between propanone molecules than between butane molecules. The permanent dipole-dipole forces between propanone molecules are strong enough to make this substance a liquid at room temperature. When a hydrogen atom is covalently bonded to a very electronegative atom, the bond is very highly polarized. The positive charge on the hydrogen atom is high enough for a bond to be formed with a lone pair of electrons on the fluorine, oxygen, or nitrogen atom of a neighboring molecule. The average number of hydrogen bonds formed per molecule depends on 1. The number of hydrogen atoms attached to fluorine, oxygen, or nitrogen in the molecule, and 2. The number of lone pairs present on fluorine, oxygen, or nitrogen. How does hydrogen bonding affect boiling point? The rise in boiling point from HCl to Hi is due to the increasing number of electrons in the halogen atoms as we go down the group. This leads to increased van der Waals forces as the molecules get bigger. If hydrogen fluoride only had van der Waals forces between its molecules, we would expect its boiling point to be about minus 90 degrees Celsius. However, the boiling point of hydrogen fluoride is 20 degrees Celsius, which is much higher. This is because of the stronger intermolecular forces of hydrogen bonding between the HF molecules. The Vsepr theory is the way to figure out what molecules look like in real life. So Vsepr stands for valence shell electron pair repulsion. You have a chart like this. What you have to do is you have to know the bond atoms, lone pairs, molecular shapes, and the bond angle as well. There's a specific procedure to figure out what shape of the molecules going to take. So, my first example is CH4. You are always going to start by drawing a Lewis structure, and you have to figure out the number of electrons in each atom. So, we know that carbon has 4 valence electrons, and each hydrogen has 1. But there are 4 of them. So altogether we end up it has 8 valence electrons. So we go ahead, draw the Lewis structure. The carbon is in the middle because it is by itself, and we're going to attach the hydrogen all the side. Our next step is to make sure each atom has its octet. Carbon does need 8 electrons around it, and hydrogen only needs 2 electrons around it. Then we have to make sure that the Lewis structure has the same number of electrons in the structure that we do the valence electron. So 2, 4, 6, 8. Then we have to figure it out the shape it's going to be, and this is based on the number of lone pair and bond atom. So we must to know the definition of domain, lone pair, and bonded atom. Domain is the number of things around the central atom, and it is going to be the lone pair plus the bonded atom. Lone pair is pairs on central atom. Bonded atom is number of atoms bonded to the central atom. For this example, lone pair is 0 and bonded is 4. So you see the chart. Bonded atom is 4 and lone pair is 0. So the molecular shapes is tetrahedron. What is the bond angle? The bond angle is the angle that is between the two atoms. It is 109.5.